Today I have the pleasure to talk about our Heckler attack, and I'd like to start with a quick introduction about confidential VMs. Now, modern x86 CPUs enable trusted execution environments with VM-level abstraction, namely Intel TDX and AMD SEV-SNP. Users can deploy virtual machines without trusting the cloud infrastructure, such as the hypervisor. And in this setting, the hypervisor is still responsible for managing certain resources for the VM, for instance, interrupts. We introduce Ahoy attacks, where the hypervisor uses malicious interrupt injection to compromise the integrity and confidentiality of confidential VMs. Our Auckland paper, VC, looked at interrupt number 29 to break AMD SEV-SNP. Now, you might wonder, what about the other 255 interrupts on x86? We asked ourselves the same question, and this led us to the Heckler paper. You've probably already heard about interrupts, and more specifically about page faults and timers, and how they break trusted execution environments. In the context they were used in, these were physical interrupts to stop the execution of a running trusted execution environment and transfer control back to the managing instance. So in our case, the hypervisor. These physical interrupts are transparent to the CVM, and what I mean by that is that they do not trigger any computation within the VM. Instead, only the microcode assist routine is triggered that exits the confidential VM. Now, in contrast, with Ahoy attacks, we use virtual interrupts, and we target the CVM directly. So more importantly, our interrupts change the control flow of the CVM. Now, I've spoken about interrupts in general. Let's take a look at an actual example, the int80 interrupt. Most of you are probably familiar with it. It's a legacy system call interrupt on x86 systems. To execute a system call in x86, the user space program stores the respective syscall number in AEX, populates the other registers with the corresponding arguments, and then executes the int80 instruction. Now, the int80 instruction does a privilege transfer and calls the respective interrupt service routine within the guest kernel. Now, in the case of int80, the interrupt handler is the system call handler, and the system call will be served by the kernel space. Now, most importantly, the kernel space will evaluate the user space registers, execute the system call, and then updates the IX register depending if the system call was successful or not. In this case, we assume that the system call was successful, so the value of IX, of the user space IX register, will be changed from 4 to 0. Once the system call handler finishes, control is transferred back to the user space, and the program continues. Now, how can a malicious hypervisor abuse an int80 interrupt in a malicious manner? Let's take a look at an actual example where the hypervisor tries to log into the victim, into the guest, without the necessary credentials. Now, in the guest, there will be some authentication routine that is called, and the result will be stored in AEX. If the hypervisor now precisely injects an int80 interrupt into the victim, it can influence the branch decision that happens based on the AEX register. And let's take a look at an actual example. This is the first Heckler attack, where we use the int80 interrupt to break the confidentiality of Intel TDX and AMD SEV-SNP. Now we have the same example as before. So the authenticate routine returns 0. The IX register is 0 in user space because the hypervisor is not authenticated. So the authentication failed. In the next step, the if statement evaluates the IX register, and it will evaluate to false because the value of IX is 0. Again, the hypervisor is not authenticated. However, if the hypervisor now precisely injects an int80 interrupt just before the if statement is evaluated, control is transferred to the kernel, and the system call handler is executed, and the syscall 0 is executed. Most importantly, the syscall handler will fail, an error is returned, or not directly returned, but the IX register is set to an error value, and the value is changed from 0 to -4. And now the if statement will evaluate to true, and the hypervisor is authenticated. Now you may ask, how can the hypervisor inject the interrupt precisely between those two instructions? Because we are still in the CVM context, and as you may know, the CVM protects its execution state by encrypting the memory and also integrity protecting it, so the hypervisor can't observe the content of the instruction pointer directly. And if the interrupt injection is not well timed, then the guest kernel will just crash. For instance, if int80 is injected while the guest kernel executes in kernel space, the guest kernel crashes. So the question that we ask ourselves is how and to which granularity does the hypervisor need to track the execution state of the CVM for the injection to succeed? And to answer the last question, even if we only have a single instruction window to inject the interrupt, we show that this is sufficient for the hypervisor to track the execution when the execution transfers from one page to another page. And this can be achieved using page-level observability by inferring the second-level address translation page faults. So second-level address translation, you might have heard of Intel EPT or AMD SLED, so the second-level stage 2 translation tables. Furthermore, we've analyzed the authentication library that is used by OpenSSH and sudo, and we found that the authenticate function and its caller are on two different pages. So what the hypervisor does is it recognizes a page fault, an execution page fault on page A. That is the call to authenticate. Then we have page B executing the authentication routine. And when page B returns, we have another page fault on page A. Now when the hypervisor recognizes the sequence ABA, it will inject the interrupt before marking page A as executable again. And most importantly, the interrupt will be injected before the test EAX instruction is executed. So there's no race condition, no timing window. The interrupt will always hit before this instruction is executed. Now there's one last piece to the puzzle. What is the actual physical address of page A and B? Right, page A and B are user space pages, and the physical address is subject to many randomization instances. So for instance, the physical ASLR in the Linux kernel, the Linux slab allocator is not really deterministic. So how did we manage to actually find the physical address of page A and page B? Now, the hypervisor, so the attack has two phases, and the first phase is the offline phase. And in the offline phase, the hypervisor spawns a clone of the victim VM, where it has full control over it, and executes this clone, collects the page faults, while at the same time the hypervisor also has knowledge about which physical addresses actually have the content of page A and page B. So the hypervisor takes these two pieces and creates a function f. And this takes about multiple thousand VM runs till the function f is stable. And once this is achieved, the hypervisor switches into the attack phase, where it now attacks the victim. And now the hypervisor has no observability of the VM and executes the guest and collects its page faults and takes these page faults, puts them into the function f, and it gets page A and page B as an output. Now, of course, it was a bit more complicated than that. And if you're interested, feel free to ask questions or take a look at our paper. Now, what did we actually break with the int80 primitive that we had? So first, we bypassed OpenSSH password authentication. And then in the next step, we also bypass sudo authentication through libpum. And since we didn't directly attack sudo, but instead libpum, all other programs that use libpum are theoretically also susceptible to the attack. And now I want to talk about signal generating interrupts, because we also looked at other interrupts in int80 in this paper. They only affect AMD SEV-SNP, because Intel TDX blocks the injection of those interrupts. And the impact of these interrupts highly depends on the application or the runtime that is currently executing. And we have here a Java snippet as example, where we have a try catch block, and the catch block catches an arithmetic exception. Now, even if the arithmetic exception or no arithmetic exception occurred, the hypervisor can inject an int16 interrupt into the CVM, and this interrupt will then cause a signal to be delivered to user space, and this signal will then cause the catch block to execute and an arithmetic exception to occur. Now we show the impact of this vulnerability with case studies on Java and Julia, where we bias the output of a statistical and text analysis tool. And with that, I'd like to quickly discuss the root cause of Heckler/Ahoy attacks, and that's that the hypervisor can inject interrupts that are never supposed to be injected externally. And that's also where one of the hotfixes tries to address this problem. So for int80, in the beginning, int80 was fully disabled on Intel TDX and AMD SEV-SNP. And on Intel, they quickly re-enabled the int80 interrupt again, because apparently it was needed by some programs for backward compatibility. And Intel has done it by, Intel TDX can distinguish if the interrupt was injected externally or if it came from the CPU, so if it was raised according to an int80 instruction. AMD can't do it, so on AMD SEV-SNP, int80 is disabled as of today. And for signal generating interrupts, they remain unfixed until today on AMD SEV-SNP. Thank you for your attention. I'm happy to take any questions.